Okay, we are titrating a 50 milliliter solution of a weak acid, 0.13 molar HClO, and our titrant is 0.130 molar KOH. All right, so this example is going to explore the calculation of pH in this region that we have termed C here. At C, we have added 30 milliliters of our strong base. So we're going to go through and we're going to calculate the pH of that. The first thing that I like to do when doing a calculation, when by the way, in this region here, the region that we are investigating presently, this is of course a buffer region for the acid conjugate base that we're calculating. And because this is in the buffer region, we're going to use the Henderson-Hasselbalch equation. This is just another way to use the equilibrium equation for, or the Ka value for this weak acid as we are titrating it. So we're going to use Henderson-Hasselbalch, and we're going to first determine how many millimoles of weak acid is in our 50 milliliters. And I've already written this over here because I like to keep up with that. I like to calculate that initially, because I know I'm going to use it time and again in these calculations. So, but just to review quickly, we have 50 milliliters of HClO, and it is 0.130 moles per liter, and that equals 6.5 millimoles. 6.5 millimoles of that weak acid. And we have just added, now again, we've just added our 30 milliliters. Write that 30 a little better. 30 milliliters of KOH. And its concentration is also 0.130 moles per liter. And that equals 3.9 millimoles. Okay. Now we are going to determine the hydrogen ion concentration of this reaction by preparing an ice table. So again, I'm going to rewrite the chemistry that is occurring, the neutralization reaction, HClO plus KOH, is going to go to ClO minus plus K plus H2O. We're not going to worry about either one of these because we know from prior discussions that H2O is considered to be constant and is not included in these calculations. And so we're going to calculate using our ICE table, ICE, which is initial change in equilibrium. We're going to calculate the concentration initially of HClO. Well, we just calculated that, right? That's 6.5 millimoles. And the KOH that has been added to this initially, but as we've calculated, we have added 3.9 millimoles, right? It's millimoles. Okay, a little hard to read that there. And what we have at the initial point of this calculation is 0 HClO. Now the change that occurs here is the HClO is going to react with that 3.9 millimoles. And so the change is going to be a minus 3.9 millimoles. Okay. The KOH is going to disappear, right? Because it's reacting. It's going to completely react with that acid. That's a strong base. Strong bases react completely with acids, strong or weak acids. That's going to be minus 3.9. And our ClO now is going to increase by a plus 3.9 millimoles. Okay, and we're going to disregard for this example the potassium in the water is not contributing to the hydronium ion concentration. All right, so now we can go through and we can do our math. We can add each column or subtract as the case may be. And when we subtract 3.9 from 6.5, we end up with 2.6 millimoles of HClO that remains after we've added the 30 milliliters. The KOH, of course, has gone down to 0, it's completely reacted, and the conjugate base of our weak acid, ClO minus, has gone up by 3.9 millimoles. All right, so now we have the basis for calculating the pH. And we're going to use, again, we're going to go back and refer to our Henderson-Hasselbalch equation. pH is equal to pKa. And we know that pKa for this weak acid concentration is 7.4. It's the pKa plus the log. And we're going to put the log of the conjugate base, 3.9 millimoles, over the remaining amount of acid, which is 2.6 millimoles. Put that in a parentheses there. Okay, and if you can go through with your calculator, and you can do that offline, you will find that the pH for this reaction turns out to be 7.57. So I'm going to put that in a box. That's our answer. Now there's one point here I wanted to bring out. I did not convert the conjugate base and the weak acid to concentration. I just use millimoles. Well, I'm justified in doing that if you think about it, because although I could do that, what I would have found, and you can demonstrate this yourself, but that the volume that you would divide each of those concentration or those millimoles by would completely cancel out. It just would completely cancel out. So really, I'm perfectly accurate in just using millimoles here, and that's why for these titrations I like to use millimoles. It saves me a step. So next time we'll do point D, which is the equivalence point, and we'll see what we get when we do that calculation as well.